Hello everyone. Today I'd like to share my research project, an optimized KNN model for breast cancer classification with SHAP-based interpretability. In critical fields like medical diagnostic, accuracy and efficiency are very important, and that's where machine learning play a big role. One simple yet powerful method is k-nearest neighbor or KNN. Optimized KNN model can achieve a very high accuracy, even up to 99.42%. However, one major limitation is that their decisions often appear like a black box. We don't know why a certain prediction was made. This is why interpretable method, sub or simply additive explanation is a powerful tool that helps explain model prediction. It has already shown great results when combined with models like XGBoost and neural network. In this study, we propose combining optimized KNN with sub. The goal is to build a model that is not only high accurate but also transparent. We combine an optimized KNN with sub to build a model that is both accurate and interpretable. We use a breast cancer classification as a domain or case study. So, how do we know this combination work? Let's look at a related study. Optimized KNN model have some promising results. For example, Chow et al. Achieve a 98.24% accuracy using Manhattan distance with k equal 14. Other studies show that with a proper tuning, accuracy can reach as high as 99.42% with a 100 recall for malignant cases, which is a very important in cancer diagnosis. Meanwhile, for model interpretability, some outperform a traditional method like a lasso. It has worked well with complex models like XGBoost and assembled neural network. Even though models like HVM can sometimes achieve a slightly higher accuracy up to 99.68%, KNN remains competitive because it is simple, fast, and when combined with SAP, can offer a clear explanation. Now let's move to the methodology, starting with the data. For this study, we used the Wisconsin breast cancer dataset. Before training the model, we performed several pre-processing steps to ensure clean data and reliable data. First, we remove irrelevant columns and check for any anomalies. Then we address missing or zero values, for example, in feature like radius mean or texture mean, by inputting them with a median value, which help preserve the data distribution. The target variable, which indicates whether a case is malignant or benign, was labeled encoded as 1 for malignant and 0 for benign. To prepare the feature, we apply a min-max scalar during the visualization pass, and the standard scalar when training the KNN model. This step is very important because KNN relies on distance calculation, which can be skewed if the features are on a different scale. Finally, we split the dataset into 60-20-20, 60% for training and 20% each for validation and testing. Once the data was ready, we trained the KNN model. We performed hyperparameter tuning using a research with 5-fold cross-validation, testing a different value for the number of neighbors, distance metrics such as Euclidean and Manhattan, and wedding schemes. The base configuration used a 5-neighbor, Manhattan distance, and uniform weighting. Achieve a cross-validation accuracy of 96.78%. Now regarding interpretability, here we use SAP, but since KNN is not a tree-based model like XGBoost or random forest, we cannot directly apply a tree explainer, which is optimized for this model. Instead, we use a kernel explainer, which is a model-agnostic approach. It works by approximating sub-values through a perturbation and prediction. Although it's more computationally intensive, it allows us to analyze models like KNN. We use a subset of 100 training samples as the background dataset to make the sub-estimation more efficient. Our analysis includes global interpretability to understand overall feature importance and local interpretability to explain individual prediction. Now let's take a look at the SAP summary plot. This plot gives us a global view of which features are driving the model decision across the entire dataset. Each dot here represents one data sample. The color of the dot indicates the feature value, red for high value and blue for low value. The horizontal position shows how much the feature contributes to the model output. Those on the right push the prediction toward malignant and those on the left push toward benign. As we can see, features such as radius worst, concave point worst, and perimeter worst are the most influential, right? Yeah, what important is that these findings are consistent with clinical knowledge. High values in this particular feature are known to correlate with malignancy. After looking at the global trends, it's equally important to understand how the model makes decisions at the individual level, especially in a clinical setting where each prediction can have real consequences. That's where local interpretation come in. We use subforce plot to visualize how each feature contributes to a specific prediction. The horizontal axis here represents the final predicted value, which is a compute from a base value. The model expected a value plus the combined contribution of individual feature. Feature on the left side of the plot, shown in blue, reduce the prediction value, pushing it toward the benign class. Feature on the right, shown in red, increase the prediction value, pushing it toward malignant. In this particular example, the feature texture mean with a value of 0.299 contribute negatively 0.02, shifting the prediction toward benign. Meanwhile, radius mean with a value of 0.255 contribute positively, increasing the likelihood of a malignant prediction. The final model output for this case was 0.646, which is above the threshold of zero point 0.5. So the model predict malignant. However, the true level was benign. This is a false positive. Now, of course, there are many factors that can influence the way a model makes this kind of decision. It could be due to the subtle interaction between feature and data imbalance, or even those in the input data itself. By using SHAP, we can at least understand and analyze this decision instead of treating them as a complex mystery. Let's now wrap up with a discussion of our research and future direction. Our optimized KNN model achieves a test accuracy of 98.25%, which is highly competitive compared to previous study. One important factor was the choice of Manhattan distance. This is contribute positively by better capturing the feature variation that are relevant for this classification task. Additionally, the model saw a good generalization. The difference between training accuracy as 96.78% and validation accuracy 94.74% was small. This is suggesting a limited overfitting. This indicates the model can perform well on unseen data. Perhaps the most valuable aspect of this approach is the balance it offers. While more complex models like SVM or deep ensemble might achieve a slightly higher accuracy, our KNN sub-framework provides both high performance and interpretability, which is essential in clinical applications where decisions must be explainable. As future work, there are several exciting directions we plan to explore. First, we validate the KNN submodel on larger and more diverse datasets to ensure its robustness across different populations. Second, we aim to incorporate a dictionary interpretability technique to further enhance transparency and model insight. And the last one, we plan to systematically evaluate the strength and weakness of different machine learning approach, including an advanced deep learning model, and assess how they compare to KNN sub in various clinical contexts. Through this step, we hope further improve performance and clinical applicability of AI-assisted breast cancer diagnosis. Yeah, that concludes my presentation. I hope this has provided useful insight on how can we combine a model accuracy and interpretability for clinical application. Thank you very much for your attention.